Hi, I'm Sergul from Biomedical Imaging Group. My thesis is on measuring functional connectivity of the brain from electrophysiological signals. Due to oscillatory nature of human brain, we need to represent our signals in complex domain. For this purpose, we first bandpass filter our signals and then apply Hilbert transform to obtain amplitude and phase information. Coherence is a widely used metric to measure interaction between two signals. And we use MEG and EEG in order to measure electrical activity on brain. However, due to limited spatial resolution of these modalities, one source might be picked up at different regions. For instance, let's say we are interested in interaction between these sources S1 and S2, but they are both reflected at channels X1 and X2, and the linear mixing is determined by the coefficients A21 and A12. If I plot the coherence between X1 and X2 as a function of these two linear mixing coefficients, you will see the spurious increase in coherence as these linear mixing coefficients increase. Let's analyze the real and imaginary part of complex coherence. Real part of complex coherence is related to the instantaneous interaction, but the imaginary part of this complex coherence is related to time-lagged interaction, which is thought to be related to the true interaction because crosstalk is thought to be occur at instantaneous range. Based on this fact, three different measures have been proposed: imaginary coherence, phase lag index, and lag coherence. If we plot all of these measures as a function of linear mixing coefficients, you will see that only lag coherence is independent of linear mixing coefficients. Let's understand how lag coherence works. Let's say our signals X1 and X2 are represented in complex domain as such, and we first project one signal onto the other one, and now we compute the residual, and finally we compute coherence between these two orthogonal signals, and this is called lag coherence between X1 and X2. However, in practice, in addition to crosstalk problem, we may have interfering signal problem, so that there might be another source which might cause an increase in the other channels. For this purpose, we came up with a novel measure called partial lag coherence. So let's represent the interfering signal X3 in complex domain. And we plot our two complex signals of interest, and we project these two signals onto this interfering signal. And then we compute the residuals. And finally, we compute the lag coherence between these two residual and call it partial lag coherence between X1, X2 given X3. We evaluate our measure using realistic simulations. We used 8 extended patches on 8 different regions on cortex where only one pair is interacting. And we applied forward model in order to simulate MEG signals. And we added some white Gaussian noise with SNR 50. And we reconstructed our signals using minimum norm reconstruction. And finally, we compute both lag coherence and partial lag coherence. And we compute true positive rate and false positive rate for each measure, and we plot them as a function of threshold. You'll see that partial lag coherence is more robust against interference and crosstalk. This might indicate that partial lag coherence has superior ability to capture the interacting edge better than lag coherence. Thank you very much for your attention.